Okay, so the 6 primary trig functions are basically the 6 different ratios you could form from a right triangle. So given the 3 sides of a right triangle, there's 6 different ratios you can form, and those define the 6 primary trig functions. And of those 6, of course we know that really the primary 2 of those 6 are sine and cosine. And so all the other 4 can be written as sine and cosine, which is helpful because most of the identities that we learn in pre-calculus involve sine and cosine. And so by being able to change the other 4, convert them into sine and cosine, then you have a lot more flexibility as to what you can do. So what is this all about? You're solving problems and you end up with these relationships of the different trig functions. And in order to make progress on the problem, it helps to be able to rewrite that expression as a different equivalent expression with these 6 trig functions. Okay, so that's kind of the name of the game, is being able to, given an expression of trig functions, write it a different way. Write it a different way that helps you solve. Okay, and so one strategy, one common strategy is to write the whole expression in terms of sine and cosine. Okay, and what makes that possible? These relationships right here. Tangent is sine over cosine. Cotangent, cosine over sine. Cosecant, 1 over sine. Secant, 1 over cosine. Why do we do that? Because most of our identities involve sine and cosine, and it's since we're more familiar with all these on the left, then working with sine and cosine is we have more versatility. It's easier to do that. Okay, I'm going to take the list down. So let's take a look on page 333. So look at A. So here's an example. So we've got this complex expression of the trig functions, and we want to simplify it. So we're going to use that strategy that I just mentioned, which is change it all into sine and cosine. Okay? So change everything to sine and cosine. So that sine x we're going to leave as it is. So leave that sine x as it is, and then we're going to change cosecant into sine and cosine. What is the cosecant? 1 over sine. Okay? And then we have cosine. And we got secant, which is 1 over cosine. So that's... So now where do we go from there? What is sine divided by 1 over sine? Yeah, so invert and multiply, right? Invert and multiply, and it ends up being sine times sine, which is sine squared. And then same thing, cosine, then divided by 1 over cosine will be cosine squared. Okay, well then what from there? Sine squared plus cosine squared. So hopefully by now we recognize our right triangle, that's just a squared plus b squared equals the hypotenuse squared. And for sine and cosine, the hypotenuse is 1. So can't get any simpler than 1. So remember what we said about an identity. Is this true for some? Like the fact that this thing equals 1. Is it true for some values of the angle x? All values. That's what an identity is. An identity is it's this equation such that no matter what x you put in there, pi over 4, 2 pi over 3, negative 2 pi, this will always be 1. Okay. So as long as it's defined, right? So for all angles for which this expression is defined, that expression will equal 1. That's what an identity is. It's not just true for some values of x, but for all values of x. That's an identity. Okay? So that's the idea of simplifying an expression. So another thing is proving an expression. So let's go down here to part C on the next page. So secant x minus tangent x quantity squared equals this ratio, 1 minus sine x over 1 plus sine x. So here's the deal with proving identities. So many of you may have done this before, and you were shown a way that I'm going to discourage, okay? So if we're trying to prove this, we want a good formal proof. So when we start this proof, or this verification of this is true, can we say that this is true? If we're trying to prove it, can we start by saying, here's the statement that we're trying to prove, and take it to be true? No, okay? The whole idea is, it's like we're not sure, it's like we're trying to take all the other stuff that we know for sure and then show that this is true. So it's invalid to use that statement of equality in the proof of what you're trying to show. So instead, what we do is you're going to pick one side. So suppose to prove A equals Z, okay? So rather than start off the proof by saying, so proof, A equals Z. No good, okay? No good. Rather, pick one side. Either pick A or pick Z. So we'll say you pick A. And we work on A. And we say, well, we can do a little bit of algebra, and we can get it to be equal to B. And we know our algebra is correct, so we're sure about this. And then we might apply an identity. And we get another form, and we get C. And we continue this way until we eventually get Z. Now, it's not going to take 26 steps, okay? It's not going to take 26, but this is the idea of it. That we pick one side of the equation, and we use algebra or other identities or known facts of mathematics to keep rewriting our current expression until we can get it to be in the form of Z. And then by this chain of equality, thus A equals Z. So A equals Z is the last thing we conclude. We don't put it first. We don't put it first because it's like we can't assume it to be true. We have to prove it's true, right? We can't assume it's true. We're proving it's true. So we can never state it unless we've shown it in the end. Okay, does that make sense? So then the question is, you come to this, and which side do you work on? Are we going to work on the left, or are we going to work on the right? Well, one kind of guideline for that is, well, what side can you do something to, right? So sometimes you look at one side and there's nothing you can do. It's the number 2. Or it's just cosine x. Well, there's little that we can do with that. So you look at the side where you can actually do some work on it and change its form. So in this particular proof on C, both sides are possible to do some work. How could we start here on the left? What could we do on the left to get started if we started with the left side? We could multiply it out, right? So this is a binomial squared. we could FOIL it, right? So we can multiply it out. What about on the right? What could we do on the right side? 1 minus sine equals cosine. Is that true? No, that's not true. 1 minus sine does not equal cosine. All right, so there is something we can do, and I want to show you this technique that you might not be familiar with. I want to do this, and we're going to start the proof here by looking at the right side first. Okay, there's this formula that in algebra that you all have seen before, a minus b times a plus b. What does that equal? A minus b times a plus b. A squared. It's the difference of squares formula from algebra. The difference of squares formula from algebra, that a minus b times a plus b is a squared minus b squared. Okay, so, and what a minus b, a plus b is the conjugate of a minus b, and similarly a minus b is the conjugate of a plus b. So this is a common technique, is to what's called multiply by the conjugate. Multiply by the conjugate, and then use the difference of squares formula. So we're going to multiply by the conjugate, and will it make more sense to multiply by the conjugate of the bottom or the top? The bottom, because as we'll see, we'll be able to get that sum of two terms eventually as one single term instead of a sum. So what's the conjugate of 1 plus sine x? 1 minus sine x. But we can't change the value of that, so we can only multiply by 1. So by multiplying by 1, we maintain the value of that ratio. So this right-hand side equals this, and so then in the top we get, multiplying out this top, we get 1 minus 2 sine x, don't forget the middle term, plus sine squared x. And what do we get on the bottom? We use our difference of squares. 1 minus sine squared x. So this expression right here is equal to the right-hand side of the thing we're trying to prove. Notice we haven't even touched the left-hand side, right? Because we're going to start with the right-hand side, and we're going to make a chain of equality to get to the left, and then therefore those two things will be equal. Okay, what can we do from here? Notice anything? Yeah, remember, so this is, I told you about this before. This shows up a lot. In the Pythagorean identity, cosine squared plus sine squared equals 1. So what would cosine squared equal? 1 minus sine squared. There it is. So by the Pythagorean identity, 1 minus sine squared equals cosine squared. Okay, what now? So here's what just happened. We just got our denominator from being a sum of terms into being a single term. And that's a good thing in terms of making some headway. What can I do with this fraction now? Anybody see? Yeah, Michelle. Tangent squared? Nice and loud, I can't really hear you. Okay, so she's saying, so with sines on the top and cosine on the bottom, can we form tangent, which would be good because it's looking like there is tangent, and we're trying to get to something that has tangent, right? So can we get tangent out of this? Yeah. Right, exactly. So just like when you add and subtract fractions with a common denominator, this is like the opposite of that, splitting it apart. It's splitting it apart. So what's the first fraction we can write? 1 over cosine squared x, and then minus 2 sine x over cosine squared, plus sine squared x over cosine squared x. Doesn't make sense. Okay, what about from here? So we may be able to keep going, but here's another technique that helps. You make some progress, but then you have no idea where to go from there. So here's another technique that helps with these proofs. Take the other side, do some side work on the other side. So let's do some work on this other side. So see if we can kind of see where it's going to meet in the middle. And then if we can see where it meets in the middle, then all we have to do is continue kind of backwards of what we did, and it'll take us to that left-hand side. So what could we do to secant x minus tangent x quantity squared? So this is kind of like side work to help us finish the proof. This is side work to help us finish the proof. What could we do with that? Well, we could do it out. So secant squared x. What's the middle term? 2 secant x tangent. So got to know your algebra. Got to know your foiling. So this is a binomial squared plus tangent squared x. And then we could write this all in terms of sine and cosine. Secant squared would be 1 over cosine squared. Secant is tangent. Tangent squared. So you really have to know all those, the ones that we wrote on the first slide. And what do you notice? Lo and behold, that's where we ended. We got to that with the blue. So now all we have to do is, we've got all the work. So now we just, starting here, we're just going backwards to our conclusion. So we finished our proof. So this is side work. So I'll put a box around it. So we know this is not really part of the proof. It's just, it helped us to finish it. The proof is in blue. The proof is in blue. So we see that 1 over cosine squared is secant squared. So here, this 2 sine cosine squared, is that what we have right here? 2 sine over cosine squared. Exactly what we have. So if we split that out, it's the same as 2 tangent secant. Did I lose you? Did I lose you? On that step or before?
On the red, honestly.
The red. So did you get this step? I multiplied this out. I squared that. So the secant squared minus 2 times that minus tangent plus tangent squared. So now I switch this all into sine and cosine. Secant is 1 over cosine, so secant squared is 1 over cosine squared. Secant, again, 1 over cosine, tangent, sine over cosine. Tangent squared, sine squared over cosine squared. But then what I found was this is exactly where we ended up, here. So all I have to do is march backwards, and I got it. Is it better? So that 1 over cosine squared, that's our secant squared. This right here, sine over cosine is tangent, leaving a 1 over cosine, that's secant. And then plus tangent squared. And now we're, instead of, so this is the multiplied out version of this factored form. So we're factoring this right here. It factors as secant x minus tangent x all squared. Therefore, that starting point by the chain of equality equals the left-hand side. So the blue is the formal proof. The red was just some work we did to help us finish. Okay, anybody have a question? Did I lose you? Please ask. Yeah? No, so the test is only through what I've said on the review sheets, right? Doesn't change the review sheet. No tangent, and only the last thing on the test is arc sine and arc cosine. Okay? So module 6 and module 7, just no tangent in module 7, but everything else.
So everything on the workbook is test?
Yes, the web work is the review web work for the test. Right. Okay, questions about this example? This is on the final though. Adam.
I know, like, when we're given like our starting equations, you said try to get things from sine to cosine, but a lot of times the hardest thing to do is like take that first step, like, okay, where do I start?
Right.
Is there any way of like looking at that besides just, is there anything helpful to where do I start?
You mean which side to pick?
Yeah, or like,
You pick the side where. So in this case, we could have picked either side. You see, we made progress on the left in the red, and we made progress on the right. But I wanted you to write to show you this conjugate technique. Okay. So in this particular case, either way, you could get started and make progress. But in certain problems, you might have like a big expression equals the opposite of cosine. So clearly, you're going to work on the big expression because opposite of cosine, you really can't do anything with that. So you work on the more complicated expression because you can actually change some things around and make progress.
okay, and then are the tools that we're going to use be just what you gave us yesterday that we see?
Yeah, well, so for these proofs, it's mostly just the 6, the right side of that. Well, no, the things on the left. Yeah, those are the main ones. Yeah. These are the conjugates of each other. So the conjugate is, you have a sum. Okay, it's getting distracting, you guys. It's getting distracting. Really distracting. Okay, so these are conjugates of one another. It's a sum, or you have a difference of terms or sum of terms. The conjugate means change the sign of the second one. So if it's a minus b, its conjugate's a plus b. If it's a plus b, the conjugate's a minus b. And so why does that help? Because when you multiply something by its conjugate, you can get it as the difference of squares. And so we see that there's all these squares in the trig identities that help us simplify things. Other questions? Yeah? Uh-huh. Uh-huh.
Isn't that like similar but different?
So what this is a minus b quantity squared. That's different. The left side of what's given is a minus b quantity squared, which is a minus b times a minus b. That's different than this. You see that? Yeah. So what's given is like this, a minus b times a minus b. Other questions? Okay, so while I take roll so you can practice, start on back on page 2, or back on page 33, number 2. Do B and C. And then work on the proofs for number 3, A and B. So the remaining 4 problems from numbers 2 and 3 on those 2 pages. Okay, you can check B and C.
Wouldn't be sin x.
Yeah, wouldn't it be sin because the denominator and the denominator is
What are you talking about?
for
Oh, yeah. I was just testing you. Pass the test. Questions on 2? Any questions on those?
Does the red come, like what is the red?
Right, how we need to add those together. How do we add that blue expression, how do we add those two together? How can we add it? Yeah. So, why did I pick that red expression?
Because, how can you just multiply
It's 1, right?
Yeah.
I multiplied by 1. It maintains the value of it. And gets the common denominator that I need. You see it? Other questions on 2? So keep going. So see if you can do the proofs on 3. That has nothing to do with the proof. But I'm going to show you that this is basically the Pythagorean identity in disguise. 1 plus tangent squared x equals secant squared x is one step from our Pythagorean identity, cosine squared x plus sine squared x equals 1. If you divide all terms by cosine squared x, you get that. 1 plus tangent squared equals secant squared. So it's another form of the Pythagorean identity. Okay, so now we got to decide what side do you want to work on? Do you want to work on 1 plus tangent squared or secant squared? Yeah, so generally the more complicated side is going to give you more opportunity to do something with, right? So 1 plus tangent squared equals 1 plus sine squared over cosine squared. Where from there? What's that? Common denominator. So we can add. So we actually want to try to add these two together and make one fraction out of it. Because one fraction gives us a fighting chance to make it be secant squared. What's your common denominator, Shruti?
So it's cos squared x multiplied with. So the equation becomes sin squared x plus cos squared x upon cos squared x.
So for the what common denominator do you want?
Cos squared x.
Cos squared. So how do you rewrite 1?
1 into cos squared.
1 divided by cosine squared? That'll change the value of it.
No, 1 multiplied by cos squared x.
1 multiplied by what?
Cos squared x.
That'll change the value of it. So you're only allowed to multiply by 1. So we want cosine squared in the bottom, but we need to keep that ratio as 1. So what do we need up on the top? Cosine squared x, right? Because it's got to still equal 1. Does that make sense? So then plus now we can do it, and we get what now? We should recognize this by now. Numerator is 1 over cosine squared is the same as? Done. So we made a string of it, and this is the way, this is a good formal proof. So what students often do, and even teachers do this too, it's just not good form. You start working on this, and you keep calling them equal all the way down. You start with what you're trying to prove, and you work on both sides at the same time. Okay? It ends up having all the work that you need, but it's just bad form because you're starting off by saying, you're declaring this thing to be true, but you've been given the task of proving it to be true. So you can't, it's an assumption that you can't make. Okay? It's an assumption that you can't make. So don't do trig proofs like this. Start on one side, work to the other. Questions? I'm going to leave B to you. Any questions on these? Okay, we're going to, let's see. So the web work, that's your review. That's the, will earn you some bonus on exam 3. That is due, to earn bonus, you have to be done with that by 11. But it's still available after 11 and then with answers. Okay, so you can still use it to study, but if you're going for extra credit, you've got to get all that in by 11 p.m. tonight. Then don't forget the post-test. The post-test, if you didn't take it yesterday, you got to take it today. Be in the door by 6:30. It's required. If you don't take the post-test, you don't get your score for exam 3. Okay, but depending on your improvement from the pre-test, I'll give you some extra credit on exam 3. So you have 2 opportunities for extra credit on exam 3. And then tomorrow, of course, is your exam. Again, same procedure. We're doing something else, so don't pack up. Yeah.
For the web work, is all of it?
No.
Only whatever you get.
Yeah, whatever you can do on it, we'll earn you some. But if you just do a little bit, it's not going to be much. Extra credit.
As far as the post test, along with our improvement over the pretest, will the post-test have some bearing on the grade?
No. So the bearing that the post-test has on your grade is potential extra credit on exam 3. Other questions? So yeah, so then tomorrow, normal procedure, bring your sun card, 10:30 to 6:30. And then our final is Tuesday night. So on Friday, I will post a list of homework problems from the whole book that will be good study problems for the exam, okay? It's a long list, but we've covered a lot of stuff, okay? So, but don't worry about the final. Focus on exam 3. Exam 3 is a big chunk of your grade, so focus your studying tonight on exam 3, which is studying for the final anyway, because that's a third of the test. And then on Friday, I'll post that review list of problems. And that's the last day I'll see you. I'm going to try to have your exams to talk about your exams on Friday. Okay? It's just that's a fast turnaround. I'm trying to get the scanning service to do a rush job. Hopefully they'll do it. And then Friday's the last day, and then I'll see you. I'll talk about. I'll have office hours on Monday and Tuesday, and then we have the test Tuesday night. Question? We're not done. We're doing something else. Yeah.
Are we going to find out what our test scores were for the pre-test?
Pre is posted. Pre is up on Blackboard. Yeah.
But what else?
Yeah. Eventually. Yeah. Don't know how long it'll take to get that. Okay. So we want to do one more thing. We'll introduce it today and do it on Friday. So remember we talked at the first day, and we defined what a quantity is. What is a quantity? How do we define a quantity? Yeah. Yep. Actually, just the quantity itself doesn't have to have units. So, but we said that in the world there are objects, and objects have attributes, and a quantity is a measurable attribute of an object. Okay? And so then we said that we could break quantities into 2 categories. Remember what 2 categories we initially said? Quantities could be what? No, all quantities are quantitative. Remember what we said? Some quantities are constant. In a certain situation, they maintain the same value, but then other quantities changing. And so we said the whole course was about looking at changing quantities, and that's what we've done all semester long. In all these different arenas, exponential functions, trigonometric functions. It was always about quantities, and especially how they change together. 2 changing quantities, how they change together. And that was our reason for functions. Functions model how 2 quantities change together. As the input changes, how does the output change? And all semester long we talked about that. So now when it comes to changing quantities, we can distinguish them further. We're going to look at a further way of distinguishing them. And so here's an example to kind of show that. So 20 grams of water is poured into a cylinder with 50 grams of vegetable oil. What's the total mass? Better get this right? 70, right? 70 grams. Okay, so a duck waddles down the bank at 20 feet. And then he turns and he swims directly out into the water, 50 feet. How far is he from the starting point? 70 feet? No, but it's still kind of like adding. It's like he went this far, and then he went this far, so we want to know kind of his total distance. But what's different in the second situation from the first? Right, we introduced direction in the second one where we didn't in the first. So what we have in the first is what we call a scalar quantity. There's no direction associated with mass. If you just add them together and get the total mass. But here, the 20 feet and the 50 feet, you can't just directly add them because each one has an associated direction with them. And so that's what we call vectors, okay? A vector is a quantity. It's still a quantity. It's a measurable attribute of something. A measurable attribute of an object. This shouldn't say quantity, it should say amount. Okay? But this quantity, it has magnitude, it has a value to it, but then it also has a direction associated with it. And we call that a vector. So a vector is a quantity that has both magnitude or amount and also direction. And then a scalar would just be a numerical value. No direction associated with it. Okay, so let's list a bunch here. So list as many, so quantities, sorry. This is difficult. Okay, so we're going to list quantities. Temperature, distance, time, force, velocity. Yell them out. What else is there? Mass, weight, speed, height is like distance. One more. Volume, great. Okay. So, which of those are vectors and which are scalars? Temperature. So let's all do. Temperature is a scalar. It doesn't have direction associated with it. So I'm going to circle those. What about time? Scalar. And by direction, we mean like in three-dimensional space, going that way or going that way. That's what we mean. So time does not have a direction in three-dimensional space. Okay, velocity. That's a vector, right? Because it's made up of speed, which is a scalar, and the associated direction. So when you take speed and give a direction to it, we get this thing called velocity, which is a vector. How about weight? Okay, it could be argued either way, but it could be a vector because weight has direction. Weight is a force of gravity on something. So your weight has direction straight to the ground. Okay, so it's actually a vector. Volume. Scalar, no direction. Distance. Okay, so displacement is the vector, distance is the scalar. So displacement is the vector. Red. Distance is the magnitude of displacement. So you take distance, combine it with direction, you get the vector displacement. What about force? Vector. Mass. Scalar. Mass doesn't have direction. Scalar. So temperature, distance, time, mass, speed, volume, no direction associated. But things like displacement, force, velocity, weight, those are all have associated direction. And we'll talk about vectors on Friday.